All right, good afternoon. Here we are yet again for another lovely session of ENGR 2302 Engineering Dynamics. Today we're going to continue with some material from Chapter 16 of the Beer Vector Mechanics text, beginning to look at rigid body kinetics. So previously we looked at kinematics of rigid bodies, and now we are looking at kinetics of rigid bodies. In particular, we are going to be studying the kinetics of rigid bodies, and what we mean by that is looking at how and why objects move as they do, rigid objects move as they do. So rigid body kinetics Namely, in kinematics, in the previous chapter, rigid bodies kinematics, we are concerned only with position, velocity, and acceleration, both translational and rotational. And acceleration. But now with the with kinetics, we will be looking at we are concerned with forces, masses, etc. So previously we were saying simply that a rigid body is just moving. We would say it's under this acceleration, or it's at this velocity, etc., etc. And we would simply say it accelerates via some agent, whatever that may be. But when we start looking at kinetics, we are considering what kind of forces or torques or moments or whatever it is actually causing this kind of behavior, this kind of movement. And we will also be working with more rigid body kinetics, in particular in terms of energy, momentum, etc., in Chapter 17 and 18 after this. But this lesson and the next will be an introduction to rigid body kinetics. So we're going to be mainly looking at plane motion rigid bodies, and rigid bodies consisting of plane slabs or bodies which are symmetrical with respect to a certain reference frame, etc. So, and we're going to be building a relationship, or looking at a relationship based off of certain equations that we had previously, namely F equals ma, famous Newton's second law, and also in the rotational sense, the sum of moments about a axis, or the equations that we had when we were looking at these equations were. We last used these when we were working with a system of particles. So we could say the sum of moments about g, where g is the center of gravity, is equal to h dot g, where this is the rate of change in angular momentum. All right. So these are going to be our guiding equations as we move through this lesson. Okay. So let us consider a rigid body acted upon by several external forces. So we'll have a rigid body with external forces applied, and this is going to be just an arbitrary rigid body. All right, so we're going to have an x, y, and a z axis here. And what we can say is we can reduce, we'll see. Okay, so we're going to assume that the body is made up of a large number of particles, which for anything made of matter, that will be the case. That the body is made of many particles. Many particles. And I can say here, well, let me draw an arbitrary system here and say we're going to have an XYZ axis. So I'm first going to draw the same arbitrary potato twice, or the arbitrary rigid body, if we prefer that. So I'll not draw the same arbitrary rigid body, but because it's arbitrary, that's okay. We're just talking a general rigid body here, and that would be the same one in each case. And consider some forces applied. So first, let's say there was a center of mass here at G. Let me draw a center of mass G here. G, and a center of mass G. G here. And let us first say let's say there are an arbitrary system of forces applied to this body. So F1, F2, F3, etc. Well, I could then say that this is equivalent to two things: a acceleration of the center of the body. So this would be an ma bar. This is equivalent to, these are equivalent back and forth, a mass times acceleration on the body, and a hg. So a torque, essentially, or a rate of change of angular momentum, or a moment. So I could also say mg, I could say there's a, actually maybe I could just say there's a sum of forces here, and then there is a sum of moments about the center of gravity. So again, I can reduce this system of forces, and this is a three-dimensional system, not a two-dimensional, but again, I can say that these arbitrary forces can be collapsed to just two things: a net sum of translational forces and a rotational force about a translational vector about the center of gravity of the object. Okay? And so we could go and find, basically what we could do is, to find F, we could just go and add up the vector sum of all the forces, and that would be equal to the sum of F there. And then to find the M, I could just find the torque or the moment produced by each of these forces about the center of gravity, and then sum up the vectors, and that would produce my overall moment about the center of gravity. And we'll have the relationship simple. We could say that our guiding relationships again will come down to the sum of forces equals mass times acceleration, like we've seen before, and of course the sum of moments is equal to a rate of change, or a change in angular momentum. Okay, and this is so this basically is showing an arbitrary system of forces on a body can be collapsed to one force and one moment. To one force vector and one moment vector. One force vector and one moment vector. Okay? So that is the general case, although in this class we are going to spend most of our time talking about plane motion, so let us discuss that. So let us look at the angular momentum of a rigid body in plane motion. In plane motion, so let us consider the angular momentum of a rigid body in plane motion. All right, so let's see this here. Oh, and we'll also define I want to remind us of a different, that will have two different reference, I want to remind us that we'll have two different reference frames we'll consider. XYZ for today will be the reference frame, the global reference frame. And G, X prime, Y prime, Z prime, or X prime, Y prime, Z prime, similar to our system of particles, is going to be our centroidal reference frame. So it is simply the reference frame point. It's not rotating or anything like that, but it is redefined so that the X, Y, and Z axis all pass through the centroid of the or the center of gravity of the body. The centroidal reference frame. Okay. Now, let's say here that I want to, I have an object, and there is a force applied, something like this. Or, let's say I have a slab here. The original origin, and then X and Y. Then I have some arbitrary rigid body. Some arbitrary rigid body, and there'll be an X prime and a Y prime axis. There'll be the G here, and the X prime and the Y prime axis, again passing through the centroid of this body. And if I look at point P here, if I want to find the angular momentum of this thing, so this would not necessarily be, this would not be a force. I'm going to look at how we build up angular momentum for a particle like this, or for an object like this. So consider a small little element of area, or a little particle P. So say we have this slab would be made of a whole series of particles P, and then, or maybe I could call this one Pi, and then I could say that for this particular piece, there is a distance from the centroid of Ri. And then, let us say that this piece had a momentum. This tiny little piece of the slab had a momentum that is V prime I delta mi. And what does this mean? Well, V prime would be the velocity with respect to the centroid. So the velocity vector with respect to the centroid, or with respect to the center of gravity, or the centroid if it's constant density, et cetera, and then delta m is the amount of mass in that little piece of matter. And so I could look at if I wanted to look at this in terms of summations instead of accelerations, the angular momentum of the slab may be computed by this. May be computed by hg, the angular momentum, so not h dot g, but hg, which is the angular momentum about the centroid, or about the center of gravity, is going to be the summation I equals 1 to n for however many particles you had. Now, in reality, you tend to use some sort of integration, not literally adding up all the particles, but in summation form, it would be r prime I, sorry, that should be r prime I, because it's the radius about the centroid rather than just the radius from the center here. So r prime I crossed into v prime I delta mi. Delta mi. I equals 1 to n. And then I can say, wait a minute, I know from earlier material that I know a way to turn this vi, the linear or tangential velocity of a particle, I know how to turn that into an angular velocity. So I'm going to do that. And that is here, well, I can simply replace this. That's not going to change. I equals 1 to n of r prime I crossed into, well, v is going to be the cross product of r omega. So omega across Ri prime times delta Mi. Then I can bring, now the omega is going to be constant across the cross section, so I can just bring the omega out. So that would be omega times our summation of, and then I have Ri and Ri squared, so that would be Ri squared, or Ri prime squared, times delta M, delta Mi. Then, however, this should look familiar. Does anyone know what the summation, or does anyone recall or remember what the summation of Ri squared delta M is? The summation of radius squareds times masses. Anyone remember what that is? That would be the moment of inertia, right? Moment of inertia. And so this simply collapses to I omega. I omega. Actually, that would just be a scalar I. Okay. Then, so again, what I'm left with is that the angular momentum of a body about its centroid is going to be equal to I omega. Omega is a vector here. And then if I take the derivative of it, take derivative, well, I isn't going to change as long as it's truly a rigid body. It's not deforming or something like that, or breaking into pieces, whatever you want to call it. Hg dot is going to be equal to I omega dot or I alpha. I alpha. So, in other words, the rate of change in angular momentum, is going to be equal to the moment of inertia times the angular acceleration in vector form. Oh, okay, so and we could look at this some more here. Results would also be valid. So this is for a slab. But I could also say that results are valid. This is also valid. Valid, really? Valid for plane motion of bodies which are symmetrical with respect to the reference plane. This is not valid now, however, this is not valid for asymmetrical or three-dimensional bodies, or three-dimensional motion. Or three-dimensional motion. What I mean by this is when I said it was a slab, I was talking about effectively a two-dimensional plane object. However, if you had, we said that there was just an x and a y axis, right? This derivation that I worked through here applies to bodies that are literally just plane figures. I assume that they were just plane figures, literally no z-axis at all. It would simply be a two-dimensional shape in the xy plane. However, this is also true, except that it must be symmetric about the xy plane. In other words, if you had a cube that was centered along the whose center passed through the xy axis, that would be symmetric about the xy plane. Or if you had imagine if you had a cylinder, but the center of the cylinder is on the xy plane. Or if you had or just an arbitrary shape, as long as it was prismatic about the xy plane, anything like that. And this also, with this, the motion also has to be two-dimensional. In other words, you can't have a a two-dimensional object moving in 3 dimensions. I suppose you can, but this equation will not be valid for that. Okay, so next we'll consider plane motion of a rigid body. Okay, plane motion of a rigid body. Plane motion of a rigid body. Okay, as we said before, we can reduce a system of forces to a moment and a force. So again, if I have my arbitrary potato body, or my arbitrary potato shape, like this, and let me draw the center of gravity on each of these. I can transform, and I have, let's say on the left one, and these are going to be equivalent forces, or equivalent systems, equivalent force systems. So say I had a variety of forces on here, F1, F2, F3, F4, however many you want. Well, I can find an equivalent system that would consist of one force, one mass times acceleration, passing through the center of gravity, and then some moment or torque around the center of gravity. And this would be I alpha. I alpha. And so, from this, well, if I have acceleration, and this acceleration can be pointing in 2 directions, it has an x and y component, so I can say that the motion of a plane body, a rigid body, in plane motion can be completely described by 3 equations.
Can you explain plane motion?
Plane motion, the question is, can I explain plane motion? Yes. Plane motion means motion in a plane.
Just in one.
In one XY plane. Or, I mean, you could define any plane you like. I mean, you could have a plane that's at a 45-degree angle or something like that, but it has to be along one axis. Not one axis. For example, it could be anywhere along the XY plane, but as long as you didn't go into the Z, it would stay plane motion. But you can define your X, Y, and Z axis in any direction you like, but it has to be sticking to, in your period of analysis, it has to be sticking to one plane. Can be completely described via 3 equations. Well, I'll have the sum of forces in the x direction equals max. The summation of forces in the y direction equals may. And the summation of forces about, or the summation of moments about the center of gravity G is going to be equal to I alpha. I alpha.
This is similar to stuff we've done in the past.
Yes, so this is similar to things we've done in the past, yes. Previously, we're looking at this mainly from the point of view of a system of particles, but now we're saying this is a continuous rigid body. Anyway, and so these systems are equivalent. Equivalent and interestingly enough, we can also say something like this. There is a principle that we may want to be aware of. D'Alembert's principle. I'm probably screwing up that French. Anybody who speaks French, did I get that approximately right? Anybody speak French? No? D'Alembert, did I get that? Did I get that? Okay, approximately. Huh? D'Alembert? Yeah. Oh. D'Alembert?
Yeah, you have to like line it with the accent. You're gonna be like, I'm in the zone.
Oh, line up the accent. So,
Yeah.
D'Alembert's.
Right.
Oh, D'Alembert's.
That's correct.
Okay, great. It sounded almost Italian or something. Anyway.
French class.
Yeah, I need a French instructor in here. Principle. The external forces on a rigid body are equivalent to the effective forces of the various particles forming the body. To the effective forces of the various particles forming the body. Of the particles forming the body. Forming the body. If I can cram this down here. Forming the body. Okay. Here. Okay. And again, in most types of problems that we'll deal with, in most problems of plane motion, and most problems that you do tend to deal with are plane motion, but there are some many cases that aren't, I guess. But whenever plane motion is always a lot easier to work with. So if there's any way that when we're doing a dynamic system that we can collapse it to plane motion, we really try to do so. Involving plane motion. We collapse all the forces, the applied forces, into one translational and one rotational force. So one translational and one rotational force. One translational, one rotational. All right. All right. Okay. And as a reminder from statics, any force acting on a body is equivalent to the same magnitude force anywhere along its line of action, or a force of the same magnitude anywhere along its line of action. Of equal magnitude anywhere along its line of action. Anywhere along its line of action. So if I had an arbitrary rigid body, and I had a force applied to it, if I apply a force to it here, this force will have a certain, let's say the center of gravity was here. Let's say the centroid was here, center of gravity was there. And this force is applied to it. This is a plane shape, and it would also have some sort of line of action. Well, I could replace that force with any force of equal magnitude with the same direction, basically lying on with the same line of action. So in other words, I could apply it here. As long as it was along the same line of action, I could apply it here. As another pushing force, I could apply it here as a pulling force. I could do whatever I wanted as long as it was the same magnitude and along the same line of action. And what I mean by equivalent is that it will produce the same tendency to rotate and the same tendency to translate. That's what I mean by an equivalent force applied to a rigid body, or to a rigid body. And that can be very useful for setting up free body diagrams and for working through various and sundry example problems. Okay, so here, and we're going to tend to use free body diagrams on these, just like we have in previous systems. We'll solve most of these problems using a free body diagram. And just as in the past, one will be a force diagram and one will be a kinetic diagram. And the other a kinetic diagram. Kinetic diagram.
Force equals ma, right? Essentially.
Well, yes, essentially F equals ma, except we'll also have to consider the rotational case. So we'll have and all of those must come to the same thing, or must come to 0. So in other words, if you might have set up a system where you have a body like this, and where, let's see. So basically all of those must come to 0, or they must equal each other, or something like that. So you might collapse, you might have one that you equate to the other, and that pretty much is it. Okay, so maybe I'll work through a more general case of this here. Okay, so the steps here, the general steps to solving plane motion. Problems of plane motion. First, I will isolate the body, body of interest. In other words, make it a free body, and replace any support forces with just force arrows. 2, draw axis system. What we were talking about this, or what I mean by this is whether you're talking about Cartesian, polar, whatever it may be. Then add in applied forces. Add applied forces, whether they be external body forces like weight, etc. 4, replace any supports with forces.
But like the resulting force of like a wall or a pin or something?
Yes, like a support force would be like the result of a wall, a pin, roller, whatever you have, or the floor, yes. Replace supports with forces. And then 5, show appropriate dimensions. And 5, show appropriate dimensions. And this would be on this is describing my force diagram, my force part, my free body diagram, my force diagram. So for example, if I was looking at a rotating wheel or something, I might have something like this. I might draw out my XYZ axis, or my X, Y, and theta, just a rotation here. And then I would probably draw out the G, show where the centroid is. And the reason for that is because my weight is going to act downward through my centroid. So this would be a force diagram. And let's say this is like a pulley or something like that that I was looking at. There might be a tension up like this here. And then I would also, if the radius of the pulley was given, and that was important, I would definitely want something like the radius here, maybe like 0.5 meters, or whatever it happens to be. So this is a very simple but complete free body diagram. Now, the kinetic diagram. So we're going to, for the kinetic diagram, we will put the inertial terms for the body on the kinetic diagram. For the body, on a kinetic diagram, let's see, and we're going to draw mass times acceleration for the particle in both x and y direction. Well, or draw the ma of the particle, if known, or of object of known. If not, keep it general. If not known, keep it general. And just write out some unknown ax and ay. And draw some unknown ax and ay. And also label a I omega. Or sorry, I alpha. And I alpha. So just like I had this system here with the weight and the torque, or sorry, and the tension, I should say, sorry, not torque. So I had this tension and then a weight here. Then I would say this is equivalent, well, yes, equal. This must come to the same thing, the inertia. So the forces must come equal to the inertial terms, which I would have my centroid here, and then max, may, and I alpha. max, may, and I alpha. I alpha. And I would also know that the sum of forces is going to be equal to mass times acceleration, and the sum of moments about g is going to be equal to I alpha. So sum of forces equals ma, and the sum of moments about g is equal to I alpha. Okay? All right, so let's work through an example of how I would draw a free body diagram and kinetic diagram out for a simple system here. Okay, so consider the bar below. The bar has mass L, mass M, and length L. A force of P is applied at the bottom. The bottom of the bar. And I want to draw out an equivalent system, or draw a free body diagram and inertial diagrams. And an inertial diagram. And an inertial diagram. So let us say I have a bar here, and it has a pin support like this. And so we're going to have something like this. A perfectly straight bar, no denser curves in it whatsoever, obviously. And let me label some points. Let's call this A, C, here's the center of gravity, G, and then point B will be the end point. And let's call this, I'll say that G is at L over 2, is at length L over 2, and L over 2. So G should be about halfway down the bar. It's a little bit more than that, but in my drawing, that's okay. Not to scale. L over 2 and L over 2. And then I have a force P applied here. Force P applied here. All right. And so then I need to draw this out, and I'll do this as such. So I'm going to replace the reaction with two forces. I'm going to label all of the forces and also draw an inertial diagram. So I will say that this then transfers to a free body diagram and an inertial diagram. A free body diagram and an inertial diagram. G and B here. And the various forces I'll have on here are, well, I'll have P, I'll have mg downward, and then I'll have reaction forces Cx and Cy. It is a pin support, so I will need an X and a Y reaction force here, Cx and Cy. And then I also might label a R here. That would be some R that I would need to look at when I was, if I'd find the moments about this, I would need, if I'm going to want to find the accelerations and such, I would need to know this R. And then this would be L over 2. Derp. This would be L over 2, and this would be L over 2. This would be L over 2, and this would be L over 2 here. And then it would be equal to this plus this, where we now have a inertial diagram. So we have our free body diagram, and notice we have all the important things we need on our free body diagram, except maybe just our x, y, and our rotation vector, rotation direction. But then we just need our inertial diagram. A C GM, or B I should say. Haha, ACGM. Well, ACGM, that's a education thing. Google it, it's a thing. Anyway, it's actually very important to this school. So if you're interested, Google ACGM. But anyway. So this would also be equivalent to the inertial diagram acting through G. Man, that is not to scale at all, is it? That's okay. MAX, MAY, and I alpha. And I alpha here. And I alpha. All right, so let's see what else. And I think maybe I'll work through one example of motion, and then we can take a break and work through another one, or some other things. Okay, so today is going to consist of mini example problems. Although, actually, you know what, I think you can take a break now. That's okay. That'll do it. So, oh, wait, question?
The moment of inertia and alpha, is it opposite the applied force?
Is the moment of inertia what?
The applied force is going towards the left.
Okay, the applied force is going to the left, yes.
And the moment of inertia with alpha.
Oh, I alpha?
Counterclockwise, yeah.
We'll be going counterclockwise. Okay. See, on here, I just generally assume unless I really know the direction of the acceleration prior, I'm not really trying to guess which direction it's accelerating. I'm just assuming it's going counterclockwise and moving up and to the right, because everything. Basically, I'm just assuming positive everything. And if I go work through it and I get a negative number, then I know it's going the other way. So, although it's up to you, it's somewhat a personal style choice. Some people like to draw their arrows, right the first time, and then they, or some people like to just make right to. Some people just like to, draw everything to the right and upward and counterclockwise. And if they get the opposite, if they get a negative number, they know it's going in the opposite direction. So two different sort of philosophies you could use. All right, but good question. Other questions? All right, that'll do it. So we'll come back in a bit and work on some more new material. Thank you.